we're being asked to find the Norton equivalent circuit with respect to these terminals A and B for this given circuit. What we notice here is that we have a independent current source that's already in parallel with a resistor. We know that we can transform that into a voltage source in series with a resistor, and all of a sudden we'd have a resistor in series with another resistance and in series with another resistance. So a small source transformation there would go a long way to help us simplify the circuit. So the best way to start in this case is to start simplifying as much as we can until either we reach the Norton equivalent circuit completely, or we simplify the circuit enough that finding the open circuit voltage and the short circuit current are easier than they'd be right now. If we're doing source transformations, we're essentially converting a Norton equivalent circuit into a Thevenin equivalent circuit and back and forth. Recall the equations that we have relating the voltage of a Thevenin equivalent circuit and the current of a Norton equivalent circuit. Also, if we're looking for a Norton equivalent circuit at the end, we should end up with a current source with a known value and a parallel resistance. Looking at our circuits, we see a current source in parallel with a resistor, and we know that we can rewrite that as a Thevenin equivalent circuit as a voltage source in series with a resistor. The value of the resistance is going to be the same, so we're still going to have 8 ohms, but our voltage source is going to be 8 times 15, which is going to be 120 volts. Thus, we'll rewrite the circuit with a voltage source in place of this current source. We also take the 8 ohms and we put that in series with our voltage source. We haven't changed any of the rest of the circuit. We still have these two terminals here, and we have the same connections here. Everything on this side is going to be the same as it was before, and we'll sketch those out very quickly also. Now we see that we have a 10 ohm resistor in series with an 8 ohm resistor and a 2 ohm resistor. Thus we can combine all of the resistance in this pathway as all in series, and so we can add all of that up. Taken together, we have a net resistance of 20 ohms. Now this 20 ohms is not in series with the 12 ohm resistor because there's another path, but if we can convert this Thevenin circuit into a Norton circuit, then the 20 ohms will be in parallel with the 12 ohms resistance, and we'll be able to combine those as well. If we want to know the equivalent Norton current, it's going to be the voltage divided by the resistance. In this case, is going to give us 6 amps. Then we'll rewrite the circuit showing this part of the circuit as a Norton equivalent circuit instead of a Thevenin equivalent. Now we see that we have 2 resistors that are in parallel, and so we can combine them in parallel. We were just using source transformations and combining resistors in series and parallel, and when we got to the end of the circuit, we ended up with a current source in parallel with a resistor, which is what a Norton circuit is, and so this must be the Norton equivalent circuit of this much larger circuit. So we were able to find this Norton equivalent circuit using simply source transformations and combinations of resistors.